Alright, so we are going to talk about 4G. And 4G is LTE Advanced. So we will talk about what is the requirement for 4G and why LTE Advanced is 4G. Then some of the new features. And this lecture, as well as the next two lectures, you will notice that these are some of the latest developments in communications, wireless communications. And so with that, let's just pay attention to these. So what is 4G? 4G is officially defined by ITU. Okay, ITU is the International Telecommunication Union, which means the telephone companies organization under UNO, United Nations Organization. And they have a recommendation called M.2134-2008, which you can get on the internet somehow, and that defines in complete detail what the 4G should do. Okay, and that was written back in 2008, even before LTE came into being. Okay, LTE came into being in 2008. So before that, they had written 4G already. And the 4G said it should be IP based. It should be 1 gig peak rate for fixed services. Things are not moving. With 100 megahertz of spectrum and 100 megabits for mobile going at 500 kilometers per hour. And they also specified spectral efficiency, how many bits per hertz you should get. Inside the cell you get 2.2, and at the edge you might get 0.6. So obviously edge is very far, cell center is very close, and peak efficiency could be 15. So when you are just next to the tower, you should be able to get 15 bits per hertz. Okay, and on the uplink 1.4, 0.36, 0.75, and so on. And then the seamless connectivity and global roaming with smooth handovers. So you should be able to go anywhere in the world, and so on and so forth, and high quality multimedia. And then competition started. Basically LTE did not satisfy it, and neither did the WiMAX. WiMAX was there in 2008. And so both of them started working on the next generation of their technology. WiMAX started on WiMAX 2, and LTE started working on LTE Advanced to meet these goals, and both of them did. Okay, so when the time came for competition, both of the technologies are 4G, except that the market and the deployed service provider, the telephone community has really adopted LTE. Okay, and so WiMAX is not going anywhere, but it is 4G. So as we noticed that 3GPP is the third generation partnership project. That's the organization which designs that designs the telecommunication protocols. First it was doing just for the Europe, now it is doing for the world. We had 3GPP2 in the United States, but now everybody is going to 3GPP, and they just keep generating new releases every year. Previously, releases were called by the year, so they have released 1999, released 2000, and so on. Then they said sometimes in 1 year they get more than one release, sometimes they don't get any release, so they got rid of the years and they got started with the numbers. So LTE is UMTS release 8. And UMTS is 3G, right? So release 8 of that became LTE, and release 10 is LTE Advanced 4G. And they keep working. Right now they are in release 14, and we will talk about that too. And then maybe release 15, 16 will become 5G. So the goal is to meet or exceed IMT Advanced requirements. And so they can produce 3 gigabits downlink and 1500 megabits, not 1.5. It is 1 comma. See, sometimes it's French and English get mixed up. So comma becomes a period and period becomes a comma. But this is 1.5 gig uplink at low mobility. It's not going at 500 kilometers per hour, low mobility. using 100 megahertz. Spectral efficiency, instead of 15, they are able to get 30 bits per hertz using 8 by 8 MIMO in the downlink, 15 bits per hertz using 4 by 4 MIMO in the uplink. Alright, these are extreme numbers. Obviously, we are not going to use 4 by 4 MIMO on the uplink, otherwise you will be carrying a truck with you. Or, you are not going to use 8 by 8 either because it costs so much, but this is possible. And DL, downlink, spectral efficiency is 3.7 bits per hertz per cell, assuming 4 by 4, 2.4 bits assuming 2 by 2, and so on and so forth. So they exceeded, basically they met the requirement. And the downlink of spectral efficiency similarly was 0. By the way, we get better in downlink because the downlink is coming from the base station. Uplink, we are tiny transmitters, so you get less, right? So downlink efficiency is only 0.12 compared to 3.7 there, right? And these are other numbers, right? So the numbers you don't have to remember, but you have to remember at least the downlink is easier than the uplink, because that is always the case, right? The MIMOs are always higher on the downlink because you have big antenna. They are difficult to do on the uplink, and so on. So some of these common principles you should know. Alright, so LTE Advanced is release 10 and it says 2011 H1. That's a notation for first half. Okay, Q is the quarter, half is H. So when they say Q2, that means second quarter. When they say H1, that is first half and the second half, right? Q1, Q2, Q3, Q4. There are 4 quarters in a year and 2 halves in a year, right? So this is H1. So before June, they got it there. I mean, before July 1st, let me put it this way, to be exact. All right. So this is 5 years old technology now. Now, having said 5-year-old technology, basically what it is that it takes 1 or 2 years to come into the market, because once the standards are done, people start making chips, this and that, and making equipment, and then deploying it. So you may not have seen too much of 4G stuff, but I mean, we have started seeing it now. It's 2016. So, but it was, the standard itself is dated 2011 first half. Continuing on the latency, less than 10 milliseconds from dormant to active. So if you're not doing anything and you need to make a call, it takes 10 milliseconds. And 50 milliseconds from camped to active. And if you're sleeping, then you will get 50 milliseconds. So it is clear that the camped is bigger sleep than dormant. Okay. Mobility up to 500 kilometers per hour, it does. And spectrum availability, flexibility, it does both FDD and TDD. Again, the last D is for duplex, right? And so it does both frequency division duplexing and the time division duplexing. Wider channels up to 100 megahertz, and it can do up to 100 megahertz wide channels, because we need to produce that 1 gigabit challenge, right? We need to meet that 1 gigabit challenge. Any questions about the requirements or the capabilities? They all make sense. I mean, like what we are talking about, right? If some particular metric doesn't make sense, or you have a question, then you feel free to ask. Yeah.
Can you please explain more about the latency?
Yeah. So this one says the latency is measured in many different ways. One is that if I try to make a phone call and it takes 5 minutes to make a phone call, which in some cases actually it does take few seconds. When I make a phone call, I don't hear the ring until few seconds. So that is one latency, right? Here it is just the latency of being able to transmit. Okay. So if you are in the dormant state, and we haven't defined what is the dormant state, right? But if you are active, you might be able to get in LTE. We know that the frames are 1 millisecond. So if you requested something within the next millisecond, you will be able to transmit it. If everything is available. If it is busy, then maybe you have to wait many frames. But if the frames are available, then the next frame you will get it. Right? So 1 millisecond. So that is a different kind of latency. So latency is measured at many different levels. One is how long does it take when you want to transmit a packet? How long does it take when you want to make a connection? How long does it take, to just get on the network? And this one is talking about getting on the network. Any other question? So what is it that, yeah, go ahead.
Why is the mobility up to 500 kilometers per hour? Why
Okay.
is that the standard?
Yeah, so that's kind of high. I mean, I have never driven at 500 kilometers per hour. And if you drive in the United States, they will give you a ticket, but in Europe they do. So, no, actually the thing is, in Europe the speeds are generally faster. I mean, you know that, right? Anybody who has gone to Europe, Germany or anything like that knows that the roads, they drive faster. But this is more for high-speed trains. So if you have really high-speed trains, which basically don't have to worry about other traffic coming in the way, they just go straight on the track, they can go 500 kilometers per hour. Okay? And you can translate that into speeds, divide by 1.6, and you get about 300 miles per hour. That's very high speed. Right? Okay? 3 key factors. By the way, when we design wireless networks, 500 kilometers per hour is not high for some applications. So I'm working on an application where we are talking to the planes. And the planes go at sometimes 1,000 miles per hour. Very high speed. So this is 500 is nothing. You know. And for that you have to worry about again same thing. You know, at that high speed, what can you do? Right? So all these UAV, I mean, I shouldn't call UAV, but all the drone stuff or all the unmanned aircraft, they are going very high speed. Alright, so 3 key factors. So basically, when you want to increase bits, there are 3 ways you can do. One is spectrum. Just get more spectrum, more hertz. You will get it. Second thing is spectral efficiency. Get more bits per hertz. Right? And that's where we can innovate. And third is the cell sizes. Make the cells smaller so that you don't go very far. Right? And that is what is happening. Basically, all 3 are happening. So LTE Advanced needs more spectrum than LTE, more spectral efficiency, better coding techniques, and smaller cell sizes. And the smaller cell sizes also give you spectral efficiency. They are related, because if you have very large cell size, you can't get that spectral efficiency. Right? So those 3. Everything that we will talk about will fall into this, mostly into spectral efficiency, because we are trying to get more bits through, and that also includes reducing the headers and efficiency and so on and so forth, right? So, okay. Bandwidth. So how do you get 100 megahertz? Well, not many bands have that much capability, 100 megahertz total. So what they do is they do carrier aggregation, which we saw before, I think somewhere in 11N, 11AC. You take many bands and you combine them together. That is called carrier aggregation. Okay? And so they do 5 carriers now, allowed now. So they take 5 bands of 20 megahertz each. LTE uses 20 megahertz. So there they use 5 times 20. 100. And they will go to 32. So by the time you get to 5G, they will be using the whole world, basically. 3.32 times 20 is 640 megahertz. Every band will be used up. And high UE power, U is the 5 throughput needed. And then if you really want a gigabit per second, you're not going to do it on your tiny phone. You're going to do it on a big computer. And so, because you will need all this power to get there. UE, everybody knows, is user equipment, right? Alright, spectral efficiency. Frequency reuse factor of 1. What does that mean? Anybody remembers the reuse factor? If you had a cluster of 7, what is your reuse factor? 1/7. Because you are using in each cell only 1/7 of the band that you bought. You bought from the government 100 megahertz, and you cannot use 100 megahertz in every cell. You use only 1/7 of it because there are 6 cells around it. Right? Here they are using frequency reuse factor of 1. Means in every cell they are going to use that. Every cell, same frequency. high order MIMO, and then of course we are going to send you 8 streams on the same frequency, same time, 8 by 8 on the downlink and 4 by 4 on the uplink. Again, these are somewhat extreme numbers because 8 by 8 on the downlink, what it says is that the UE will have how many antennas to do 8 by 8 MIMO? How many antennas on the UE? Nobody knows? To do 8 by 8 MIMO, how many antennas do you need on the transmitter and how many on the receiver? 8 by 8 means you need 8 on the transmitter, 8 on the receiver, right? You can have 8 by 4, where 8 on the transmitter, 4 on the receiver. So 8 by 8 MIMO, you cannot do on your tiny phone. I mean, not today, at least tomorrow you will be. So the thing is, that is what it needs on the downlink and 4 by 4 on the uplink. So you are transmitting 4 antennas and they are receiving on 4. New MIMO techniques. So they have some new MIMO techniques that we will talk about. Inter-cell interference, coordination and cancellation. We will talk about all of these. These are the new features that they have developed to increase the efficiency. And the cell sizes are multiple sizes, so they have relays like we saw before in 11s. We had the main access point and the relays. So we have those, and then we have something inside the home called home node ENB. ENB is the evolved node base station. So home ENB and relays. So all of these things, these are the techniques. So carrier aggregation. Carrier aggregation, basically whatever you got, we will take it. So if you have these 5, we can take 1, 2, 3, 4 and combine them as if they were 1 and 3 on the other side. So the number does not have to be the same on both sides. Okay, so this one shows downlink 4, uplink 3. And this is backward compatible with LTE single carrier. So if there is an LTE device here which does not understand multiple bands, we'll just go on the first band. Or whatever is called the central band. So main carrier, it doesn't have to be first band. So we'll go on the main carrier and then we'll ignore all other bands. So each band itself does not have to be 20 megahertz. It could be 1.4, 3, 5, 10 or 20. Okay. And these numbers 5, 10 or 20 are clearly easy to understand because 10 is half of 20 and 10, 5 is this. But then they don't have 2.5 and 1.25. They have 1.4 and 3. And these numbers came about the previous life allotments. So in 3G, when you got the allotment, sometimes you got 3 megahertz, sometimes you got 5 megahertz, sometimes you got 1.4 megahertz. So they just took those numbers and say, okay, we'll use it for LTE Advanced. So basically all of these are not in the same frequency band. Some might be in the GSM band, some might be in the 3G band, some might be in the 4G band, and you can combine all of that. So 1.4, 3, 5, and 10 and 20 megahertz, each band can be that much. But you can have maximum of 5, and if you have all of them at 20, then you get 100. Right? To get 100 megahertz, you need to have 5 times 20. Each component can be different width. So it doesn't matter really, they don't have to be, for example, so far we have seen in 11 AC, we had 2 times 20, or 2 times 40, or 2 times 80, the bands were kind of equal, and then we kept dividing by half. Here, this basically we announced what is the size of the width, width of the band, and so it could be anything. And the numbers of components in the downlink and uplink can be different, but the downlink is generally more than the uplink, because base station is generally more capable than the UE. Alright? Having said that, generally, because it's quite possible that you just bought this latest smartphone which is capable of 5 thing, and then you went to some worst country where they just had LTE with 1 carrier, so the downlink would be 1 and the uplink would be 4, you won't be able to use it. But when you are using it, uplink is always less than the downlink. Equal to is possibility too. So it doesn't have to be less. It could be less than or equal to. Right? Because if you got it, if suppose you have 5 and I have 5, there's no reason for us to use 4 and so on and so forth, right? So, and generally the uplink traffic is less. That's another thing. So uplink is not only difficult because the UE does not have big transmitters, it also doesn't have too much traffic. Right? We download more than we upload. So the need is more, capability is more in the downlink. Any question about this carrier aggregation? So the components can be contiguous or non-contiguous. So contiguous means next to each other like this, or non-contiguous means far away from each other like those. Now I don't remember this, but I think in AC, all the charts we saw, they are contiguous. We saw 160, 280s and so on and so forth, right? So here they went one step ahead of that and they said, we'll just tell you where they are so you don't have to worry about whether they're next or not. And there could be different cell sizes too. So this one is a bigger power and therefore has a bigger distance, bigger cell. This one is medium power, has a medium cell. This one is low power, has a lower cell size. Right? And why they are different power? Because every band comes with a power limit. Right? Every one, when government gives you, they say that 900 megahertz you cannot use more than this, 6.5, 5.8, whatever. They give you a power limit. So depending upon whichever is the highest. And second, okay, all right, there is more thing too. It's not just the power, it's also the wavelength. Some wavelengths go far, some wavelengths don't go that far. So that is not shown here. But if this was a small wavelength red, this will probably go far. Okay? And so given the power and the wavelength, you will figure out what is the cell size. And then the directionality, how much directional you are. Because if you are very directional, then it will go in one direction, otherwise everything go in the circle. So each component carrier has a serving cell, and the size of the different component carrier cells may differ. Okay, so you can see right there are 3 carriers and 3 cells. Phi, MAC and RLC, radio link control. Phi, MAC and radio control are all extended to handle varying number of components. So everything knows that, okay, I'm 5 mile Phi, I'm 3 mile Phi, I'm 2 mile Phi. Depending upon that, they will select the right modulation and everything else will change accordingly. Large buffer in RLC to accommodate large data rate. And because now we are going to get 1 gigabit per second, we need storage to store things which are coming out of order, are not able to go, and so on and so forth. The buffering goes up too. So all of this is handled correctly. So much about carrier aggregation. Any question about carrier aggregation? Okay. All right. MIMO. So 8 by 8 in the downlink, 4 by 4 in the uplink, and MIMO is used only when SINR is high. What is SINR? To? What is I? Interference and noise. Okay, so what is noise and what is interference? Anybody knows? Remembers? Yeah, okay, go ahead. Go ahead.
Interference is when we have like some subcarrier interference, but noise is just in the environment.
Okay.
Because it's the thing that we cannot cancel it, but we can have some method to cope with the interference.
Okay, what do you want to say?
Isn't noise typically like same level across all the whole spectrum, and then interference is spikes at different parts?
Yeah, so generally interference is just another transmitter. It could be yourself too. Like she said, it is inter-carrier interference. In that case, you are the transmitter and your carriers are interfering with each other. But it could be just another base station nearby. So they both are transmitting. So that is interference. On the other hand, noise is what is happening. The sun is shining, so there is a noise, and then somebody is doing. So those noise things are very random, and they are not consistent, whereas the interference is consistent. I mean, if you are in an interference area, you will get that consistently because both are transmitting, right? So another transmitter is interference, and the noise is various different reasons, other things which are happening in the environment, which is just the heat, the temperature, so on and so forth, which will cause radio transmission. Okay? SI and R, so that includes both. SI, you take the signal, you take the interference, you take the noise, signal divided by interference plus noise, that's the ratio, SINR. If it is low, if the noise is low and the interference is low, then you don't need to use MIMO. You can just go ahead and use straight. If SINR is low, other spectral efficiencies such as transmit diversity are used. And transmit diversity is actually another form of MIMO basically. I mean, it's slightly different in what you do once it gets inside, but transmit diversity means you transmit multiple channels. Many different transmission modes are defined. U is informed about the mode to use by signaling. So basically now you might have, if nothing else, you might have different MIMO levels. So I'm transmitting 2x2 to you, 4x4 to him, and 64 QAM, 32 QAM, and everybody is different, right? There are many different modes, and we tell you what we are going to use for you. Modes differ in number of antennas, antenna ports, precoding type, and type of reference signal. Reference signal is actually, we have called it pilot before. Okay? And so all of these could be different, and so that is what the mode is. 3 new categories of UE, category 6, 7, and 8, and category 8 supports maximum features. So now what they have is actually, by today, they have I think about 14, 15 categories. By this time when this was written, there were categories 8, category 1, 2, 3, 4, 5, 6, 7, 8. Alright. And category 8, generally higher the category, more expensive, more features. So the user equipment tells, okay, well, I am category 8, and therefore now we can use lots of MIMOs and everything else, right? So category 1 is cheapest, and they don't do much, and so on. Category 8 supports the maximum features. Alright, any question about MIMO? Then precoding. So we saw the word precoding when we were talking about single carrier frequency SCFDMA, where single carrier was nothing but precoding before WebDMA. But you can do something else with precoding. What you can do is, when you have a data, you can put some reference signal on the data. That means this is exclusive R symbol. The exclusive R with CRS. CRS is the cell reference signal. Okay? And then you transmit it. At the other end, you will remove the reference signal, and then you will get the data. Alright? So why you do that? Basically to make this transmission more random. Because if the transmission is all zeros, it will have disaster, because all zero could mean low values all the time, which would not be good. So you make it more like this, which is much better than all one level. So anyway, so there are two kinds of CRS, codebook based and non-codebook based. Codebook based means there is a formula. Non-codebook based means demodulation reference signals are added before precoding, and receiver can infer precoding from the pilots. So this one basically comes from the pilot, non-codebook, and codebook means there is somewhere a table. There is a table that is called codebook. Okay, and another difference is whether it is done before or after this box. In this case, this is done after precoding, and this one is done before precoding. The signal is added before this. So this is it says are added before precoding. So this is before precoding. This is the non-codebook based. And so at this point, all you have is the pilot signals, and you just somehow add the pilots and you get whatever you need to do after that. Anyway, so this one basically, the key function here is to randomize the signal, either way. Alright, now if there are no questions, then we can move on to coordinated multi-point operation. And this is to basically, this is called COMP or COMP, and COMP's function is to do the interference reduction. Not the noise, but the interference reduction. So here is the problem. You are in a cell, which is, and the cell boundary of red and blue, this cell, this is getting signals from both, and almost equal signals from both. There will be a lot of interference at the boundary. We are using the same frequency. Right? So what do? We tell the other guy that, look, I am taking care of this guy. Can you please not do this? So I will talk to him at this time. During that time, please don't transmit in that direction. Okay, that is called coordinated multi-point operation. Okay, so now let's see more detail. So to improve performance at the cell edge, base stations coordinate transmission and reception. Joint transmission, multiple transmitters in the same subframe, dynamic point selection. So now here's another thing they could do. They could say that we want to sell this packet, I want to sell this packet to this guy, and can you please also send the same packet to the same guy? Okay, so there are joint transmission. Two base stations are transmitting the same signal to the same unit. So that we interfering there somehow, it is getting two copies, and somehow able to distinguish between the two copies and make all the corrections and errors and so on and so forth and get better reception. So that is one way, right? Joint transmission, multiple transmitters in the same subframe. Now remember, the frames are all coordinated. They are 1 millisecond subframe, and if the clocks are synchronized, then I will say, okay, on the 5th subframe I'm going to send it, you also send it in the 5th subframe. Okay, things like that. Dynamic point selection. Transmission is scheduled from one base station. So dynamic point selection, basically this means that you don't worry about it. I mean, I will do your scheduling for the 5th frame, because I'm going to do 5th frame for this guy, and I will schedule yours also. So that is another way, is that transmission is scheduled from one base station. So one base station takes charges for both, for that subframe, not for everything else. Joint reception, and then same thing. The base station, the mobile transmits. It goes in both directions. Both of them receive it, and both of them then send to each other and figure out. You have a question?
Yeah, I just have a question about the joint transmission.
Yeah.
So, like, two or more transmitters would send to like the same receiver.
Yeah.
And how does that, like, does it combine them, or does it receive it like sequentially? Like, how does that?
Okay, so basically, if you have any MIMO kind of thing, then you can clearly distinguish between the directions. Right? So you can see that this signal is coming from here, this signal is coming from here. Right? And then you can decode them separately, and then you can do error correction. Just like we talked about in the HARQ and ARQ and HARQ. Joint reception, joint transmission, point selection, and UE is informed about different UL-DL decisions. So whatever you are doing, you tell the UE that this is what we decided to do. You are the boundary. Now you are in charge of, you have two bosses in charge. Listen to him, listen to me.
But that's in case.
Eh?
That in case that the UA is fixed.
No, so it cares. No, it cares. I mean, if you are category 8, maybe you can do this. If you are category 1, you cannot do it. So it does care what the UE has the capability or not. That is the first thing we check.
No, I mean for the mobile UA.
So?
How would they know that it will be at this location?
Oh, okay. The question is, how do they know where the location is?
No, I mean, it's a predefined that at time frame, 5% to this.
Yeah, all this is done. See, this is one thing, it's very complicated. Yeah, but it is done in the sense that every millisecond they decide who will talk in the next millisecond. So it's not set up like before in GSM or something where you got the fifth channel and you have that fifth channel for 10 seconds or 10 minutes. Right? Here, every millisecond they decide who will speak and which carriers they will speak on and which half time, because a slot is half millisecond. There are 2 slots in a frame. Right? And there are 1024 subcarriers, and you get only 12 or some multiple of 12. So there are lots of decisions to be made about who will speak. But all of this is done at the speed of light, and so you don't see it, but this is happening. And as soon as the mobile hears that I have gotten the carrier from 15 to 23 or whatever, it just gets ready for that. It does the calculation and transmits on those carriers. So everything is very dynamic. So UE is informed about the different UL-DL decisions and about who is going to transmit. But this is called COMP, Coordinated Multipoint Operation. And this is also actually, it doesn't say on this slide, but this is also helpful for broadcast. If we want to broadcast anything, we want to give it to everybody, then obviously both the channels will say, okay, like on the 5th frame we will do the broadcast, and they will broadcast. If it is a TV, if it is burning, it is anything, everybody will receive everywhere. Right? And so, but here we are talking about at the cell edge, how do you improve the interference? Okay. I think one point to emphasize is by looking at this figure, that what this is saying is that these are little things, are slots or frames or whatever you want to call it, subframes, and in each subframe there is both red and blue. Okay, this is red, and this is blue, right? In this case, the scheduling is slightly different. In this case, they divide the whole frame. So they say, okay, like first 2 frames are subframes are yours, next 2 are mine, and so on and so forth. So they can do that way too. They could just multiplex on the time or share the time. Yeah.
Could you explain the joint reception? How it could work? Like
joint transmission.
No, joint reception.
Joint reception. Multiple BS receive the signal from one UE and combine. Okay, so all these E and Bs are connected in the back, right? Right, so they can hear each other. They actually talk to each other quite a bit because of the handover on the back hall. Okay, so joint reception, you just change these arrows to the other direction. So they will both receive the same transmission.
But the UE will send one time or multiple times. How many times can it send the same signal?
And both are possibilities. Both are possibilities. I mean, the UE could be directional, in which case it has to send 2 in 2 directions, or it could be omnidirectional, in which case it will go anyway, both directions. So somehow both will receive it, and then they will compare the notes in the back hall, in the background.
I didn't understand how UE can send multiple signals.
Yeah, right. So multiple signals 2 ways, right? 2 is like 2 transmission and 1 is 1 transmission. And the answer is both possibilities. Yeah, you have a question?
So for the joint transmission, I think that okay. So for the joint transmission, the transmitters here, by the transmitter here, you mean the multiple UEs or multiple BS?
BS. Okay.
I think
Okay. So here when we said, okay, hold on.
BS.
Okay, hold on. Multiple BS receive Okay, here multiple BS transmit. So so we talked both directions, right? In the downlink and the uplink. Here it clearly is multiple BS receive. The transmitter is the UE. And the next question was asked, is that one transmission or two transmission? Basically, if the E and B are smart enough, they could schedule in one subframe and say, okay, just make one transmitter. So that's why this is coordination, right? So they could schedule you in that subframe and then you transmit, it goes both directions. You cannot speak to a base station unless they schedule you, right? So if they don't do that, then they will say, okay, all right, on one frame 1 you transmit me, and then on frame 3 transmit to that base station. So everything is coordinated. Yeah.
Yeah. In the joint transmission, if the two BS can transmit the same data to the UE, so they should get the same data from
the backhaul.
So
Yeah, that happens too.
Yeah.
Yeah. See, the thing is, because they all have connection in the backhaul to some MSC or whatever we call it, main switching center or something, right? So the data can go two ways from MSC to two towers. Generally it does, because the handover it needs to be done anyway. So when you are at the edge, the data starts going to both directions. You may not be able to listen to the next tower, but the data is there. And as you go and then you give up this tower and take that tower, your data doesn't get lost because it is at both places. It's very complicated. I mean, compared to IP is very simple. I mean, there everything was what we call distributed. Here everything is centralized. Okay. So the main MSC or whatever, that is central unit that decides that which tower is in charge. The two towers are in charge or one tower is in charge, and then they talk to each other and they do this. Everything starts from the boss, goes down to the downwards, right? Whereas in routers can make independent decisions in IP, and so we are coming from IP world. We are the net heads, remember, and so our thinking is very different compared to bell heads. Okay. So relay nodes. So the relay nodes are, we have seen relay nodes before. These are low power base stations and used to enhance the performance at the cell edge. Hot spot areas are indoor coverage. So wherever the coverage is poor, you put a little tower, put a relay. And you understand the difference between cell edge, hot spot. Hot spot is if there is a big downtown, there are lots of cell phones, you cannot serve from one tower, you put a little tower there. That's a hot spot. And then of course indoor coverage, if people are in the basement, how do? You just put something in the basement. Okay. Donor E and B is the primary base station. So for whatever reason, they selected this name, donor, which I don't understand. But anyway, this is DE and B is the main base station, and this is the sub base station. This is the donor cell, and this is the sub cell, right? Primary and secondary. This would have called primary and secondary, but anyway, donor. And then the donor E and B is DE and B. Okay. A modified version of EU Etran interface, UU is defined, UN, for the relay nodes, and both donor and relays may use the same or different frequencies. Now this is another little complication. So the relay nodes don't have their own frequencies. If you are using whatever you got from the government, the whole band, you can give it to you can donate it to the relay node, and relay node will use the same. So now we have the same problem as before, that this is going to hear from relay node as well as from the regular node. Right? So there is a cell edge interference. Again, they will coordinate, just like before. So first I taught you about coordination. Now that coordination was among the two towers. Now here is between the tower and the tower's son or child or daughter or whatever you want to call it. So So the relay and the main tower, they coordinate. Again by the same methods, where one may transmit, both may transmit, one may not transmit when the other is transmitting, things like that, so that things work out. Both donor may use the same or different frequencies. Self-interference. Relay transmission may interfere with its reception on the same frequency. Now here the thing is that it may transmit and then it may not be able to receive because from some other people they are transmitting on the same frequencies, but they are not attached to it, and so on. So avoid using time sharing. So what they do is everything is scheduled again centrally, so that when somebody is transmitting, nobody else is transmitting. Period. You know, whether it is the relay node, main node, or the UE or other UEs. And avoided using time sharing. Donor does the mobility management. Now here I think the main base station still does the mobility management. What is mobility management? Mobility management is handover. Okay, so if you're going from the relay node to another tower, or you're going from relay node to the main tower, or you're going from one relay node to another relay node, all that is handled by the boss, which is the main base station. Okay? Yeah.
So in one donor cell it could be many relays?
Of course. So a donor cell could be very large and could have many hot spots, could have many basements, could have many relays.
And they might interference to each other.
So the question is, if there are two relay nodes, can they interfere with each other? Yes, they could interfere with each other. And again, that will be taken care of by the donor node, because what will happen is the UE reports everything. UE says, look, I am hearing from this, and I am getting this much strength from here, this much strength from here, and so what should I do? So this comes like, okay, all right, you talk to node 2 and don't talk to node 1 anymore. It's a handover, right? So they can be handed over from one relay node to other relay node. And then the coordination will happen same way. Like now at that point where the the UE is at the edge of the two tiny cells, right? They will have to coordinate. Yeah.
I think that they could really know other places that they won't interfere too much, because they use relay nodes to straighten the signal. So we use them when the signal is too weak. So it means that there wouldn't be so much interference.
Right. Yeah. So the thing is, here's the thing. They put the main base station also just like that. Is that they do the geographical survey, and then they figure out that here the signal is weak. So I need the second base station. Same thing for the relay nodes. However, having done that, there is still a boundary. Even whatever you do, there is a boundary.
Well, I think it's not too severe.
Okay, hold on. So let's say we put 2 miles apart in the base station, exactly at 1 mile from the two. I don't know what you mean by severe, but there could be interference from one or the other. I mean, you cannot have at 1 mile so that only one is coming, other is not coming, unless they both coordinate. Okay, so the edge interference is there. So what it is, I mean, there is always an edge. Right? And so that's why they have to do the coordination for the edge. Yeah.
So what's the difference between E node and donor E node? Do they coexist?
I'm sorry, donor node and what?
And the E node?
Relay node.
Yeah. No. The E node B.
Oh, E node B. Oh, okay. Actually, I think there is no difference. E node B normally be used so far without the relays. Now the D, E and B has this extra piece of software which allows it to handle the relays. It's just extra function.
So E node.
E and B and D, E and B.
They can coexist.
Oh yeah, they always coexist. Yeah. I mean, in the sense that for the rest of the cell here, this D, E and B will be just working like a E and B. For that little area over there, For people in that area, it will coordinate. This is just an extension for that little area.
The
Yeah.
relay nodes don't do any coordination among themselves, right? They send the information back to the donor node.
Yeah, so generally, so here's the thing. Basically, everything is centralized. So you tell the boss, and the boss tells you. In fact, when we say DENB, I think when the DENB goes to its boss, okay, which is the MSC. So lots of decisions are made there, and it has to go to MSC because here it can make a decision because the relay node is in control. But what if somebody is at the edge with the other base station, right? Then it has to go to joint boss, right? So things are centralized like this. All right. So now we have what we call heterogeneous network, HetNet, and small cells. So the relay nodes can be of many size. It could be macro, which is the normal size. It could be micro, smaller size, or pico, even a smaller size. So now we just don't have two generations. We said main and the relay. Now we could have children's children. Okay. So now we have E and B, or DE and B, and then there is this micro cell, or there is a femtocell. Femtocell covers one home, one house. Right? And microcell may cover a mall, some bigger area, not just one.
Neighborhood.
A neighborhood, a mall, a big hospital, something like that, okay? Yeah.
About peak.
Okay, so now the next slide will talk about different sizes, but these are not very standard. Just think about this, is that there are big, small, medium, large, small, all sizes are there, right? And so we talk about macro, micro, pico, femto, nano, you can name whatever you want. So there are all sizes, but the theory is same. One thing which is fixed is a femto. Okay, femto is a home. So when we talk about home, it is different than the rest of this stuff, because in the home, security is a big issue. So if they send me a femtocell, I can open it up and I can modify it and I can start stealing, right? Which I cannot do in the mall. Generally, we can trust the mall guys. Right? So femtocell has some special considerations. Other than that, everything is, public domain. So HetNet. First of all, you heard the word HetNet, which is the heterogeneous network, which means that more than one base station. So here, this one is this particular one. Well, so basically there are two cells here, the macro cell and then the small cell. So they are using the word small, which could be macro, micro, pico, whatever, right? So a small cell simply is a general name for a child. So the UE selects the BS with the strongest signal in the downlink, and both BS have the same SSDL at the edge. SSDL is the strongest signal. SS is the strongest signal in the downlink. So it measures the power and it says, okay, I want to go with that. So this UE, for example, when it is here, inside the dark red, it will clearly select the relay node. When it is in the white part of the cell, it will clearly select the donor and DE and B. But in here, it could basically, normally it would go with the donor E and B, right? But with some coordination, this relay node could be told that, okay, all right, can you please increase your power a little bit in that direction? So it could do that too. So it can, just to cover this UE, it does this, and so now UE is covered by the relay cell. So these boundaries are somewhat flexible. Alright, so this is called cell range extension, CRE. Cell range extension allows a small cell to serve more users by requiring users to join the small cell even if the power is slightly below the macro cells. Here the user is told, look, I know you are getting more signal from this big one, but please don't come to the big one. Stay with the small one. Alright, so that is called cell range extension. Yeah.
Why they name it as heterogeneous?
Heterogeneous because they're not the same size, same power. Heterogeneous, not homogeneous. So HetNet is same thing as small cells. Basically, sometimes they say small cells, which means that basically there is a big cell and there is a small cell. And so now what this is showing is that along this ellipse, SSDL small is same as SSDL macro. So if you were to measure the power here, it would be the same. Strongest signal would be same. But this one, where the strongest signal clearly is higher from here, is going to talk to this one, not the strongest signal. Okay, that is called cell range extension. During the cell range extension, you will talk to the weaker guy because just you were told to do so.
What's the advantage of this? What's the advantage?
Advantages? Oh, this is load balancing. Actually, I mean, what it is that the DENB is taking care of 1,000 people and just cannot take one more. So it just gives that out to its children that please handle this load balancing. Actually, I think it appeared in your presentation somewhere where there was load balancing and handover. This is one of the ways of load balancing. Is that the load balancing generally should be so that you go to the strongest signal, but they said no, there are exceptions. In which case, we will tell you that to go there only, stay there. All right. So now we talked about what about the cell sizes. So cell sizes are macro, micro, pico, femto, atto, jepto, and I can't remember, what powers are what. Okay. So don't even go by 10 raised to minus 6 is actually, that is micro that we know. Okay. 10 raised to minus 12 is pico and 10 raised to minus 15 is femto, but that has nothing to do with the cell sizes. It just, they go smaller. Okay. So a picocell is not a millionth of a microcell. Okay, neither in the radius nor in the area. It's just a small, maybe factor of 5 or 10 or 20 or something, right? But they just gave the names like that. Okay, and none of these are standard names except for the macro cell, which is the standard cell, and the femtocell, which is in-home, and then pico and micro could be any size. Okay, except that micro is bigger, pico is smaller. So pico is generally used in building with public access, which means like a hospital and so on and so forth. Microcell is a neighborhood and public access, malls, train stations, and so on and so forth. And attocell in room and jeptocell on desk. I have never seen those two. So let's not worry about it right now. Okay, there are no million nano. That's another thing I noticed, that they skipped some things here. They went straight from macro to micro, skipping the millicells. And they skipped the nano. Well, pico is same as nano, isn't it? Pico. Nano is 10 raised to minus 9, is it? 12. 9. Okay, so they skipped 10 raised to minus 9. Alright. So, yeah.
The attocell, is it like Wi-Fi?
Okay, so here we are not talking about that at all. We are still talking about straight LTE coming, and I haven't seen a straight LTE in a room yet. So we are not talking about Wi-Fi. Okay, there is a whole module there is a whole slide on Wi-Fi thing. Right now we are talking straight LTE. Okay, so the idea is femtocell. Now how the femtocells work is that in the femtocell the backhaul is by DSL. So it doesn't go from here to there by air. The femtocell just covers this little house. If your cell phone is here, you talk to the femtocell base station, and whatever it gets, it sends it by internet to the tower, not by the air, by wire. And whatever comes from there, it comes by the wire, and then it transmits it back to you. You see the point? That the backhaul is not by the air, it is by wire. Only the first hop from UE to the base station to the femtocell is wireless. But then it goes over the wire on your own DSL. So you connect it to your DSL. Okay? That point is clear? And if your signal is bad, I mean if you're not able to get signal in your home, you can buy a femtocell for $270. At one point I thought of buying one, but some companies will give it to you for free. So right now I have one for free, and it has nothing to do with Wi-Fi. Basically, so actually I think the one that I have does not have the backhaul by DSL. It is front haul and the backhaul is both by air. And the one that I have works like this, that I have two units like this, and one I sit and put it near the window, so it has a good reception, and then that one transmits it to the central unit, which is my base station. So it's all by the air. Does not use Wi-Fi, does not use by internet. So there is some transmission between those two units, and what band they use, what protocol they use, I don't know, but they don't use my Wi-Fi. Okay? Alright, any questions about these types of cells? So femtocells, 50 to 100 meter cell radius, indoor, residential, small office, SOHO. SOHO is the word for small office, home office. SOHO. SOHO. Backhaul over DSL, plug and play. So now because it is at home and people have no idea of wireless 4G, 3G or anything, so they are plug and play. They just send you a mail and you plug it into power and that's all you do. Okay? They are self-organizing. So if your neighbor also got one and you got one, they are not going to interfere with each other. They are self-organizing. They will figure out that the neighbor has one and you have one, and they will somehow, talk to the boss, figure it all out. Okay, self-organizing, self-optimizing. They do everything, so you don't have to program anything. Omnidirectional antennas, they are very simple with no sectorization. 10 to 50 users, 10 to 40 megabits, low cost. Defined user groups. Now that is another thing, is that they are not serving the public. So the phone company might even build in the phone numbers that, okay, you and you can talk, or certain people can talk through that. So the defined user group. Continuation of macro network and handover of calls. So this is basically calls will be handed over, which doesn't really work very well. But if you start making call inside the home and walk out, the calls will not get disconnected. It will be handed over to the main tower. Right? But just yesterday my wife complained. She came out from outside talking to somebody, and as soon as she entered the home, the phone called to somebody. Oh, I got into the home. So this doesn't really work at that much. But it should work basically. Regular mobile equipment work in the femtocells, and so you don't have to change anything in the equipment. Equipment understands. They just talk the same protocol. And the multiple femtocells should coexist, and they understand that every apartment in a big building will have its own femtocell. So that's not a problem. New applications, HD video streaming, LAN services. Now because you are so close to the tower, you can get high speed, and then you can do high speed stuff such as video streaming. Yeah.
So I would like to ask, what about the signal that the phone can connect to Wi-Fi and get signal for the Wi-Fi?
Yeah, so that's a different technique. We'll come to that at some point. I think we will talk about that. That's another technique. So far we are just talking about, everybody is talking LTE only. They don't speak Wi-Fi. They're all using licensed frequencies. They're not using 2.4 gigahertz or 5.8 gigahertz here so far. Right? There's another technology which uses Wi-Fi. So what does self-organizing mean? Self-organizing means that basically the lifetime of a device, and this is for any device, is you have to install it, then find out where you are, and then do the configuration, and then you come do the measurement, and then optimize it. If something breaks down, you can do the healing again, and you keep doing throughout your life. Basically, throughout your life, you do the measurement, optimize yourself, and heal yourself. And keep doing it. That is called self-organizing. So, no, basically, self-organizing means that we don't need you to go and punch the buttons or do anything. All the logic is built into the device. So, user installable. So, I have 70 million Femtocell expected in 2012, right? So, non-physically accessible to the carrier. So, actually, I think this number may have been overstated because there was in 2012, we all expected to have Femtocell in every home. But this Wi-Fi technology came in, which he's talking about, that really gets rid of whole Femtocell. So when I called my phone company and I said, I need this thing, he said, no, why don't you try Wi-Fi? I said, no, I don't want to try Wi-Fi. Send me the cell. So when I insisted, they sent me. And then I said, okay, give me Wi-Fi 2. So I got Wi-Fi 2. And actually Wi-Fi works much better. Okay, but that's a different technology. So there was a point when Wi-Fi was not thought about and they were thinking about Femtocell. But the Femtocell revolution has been hurt by this Wi-Fi integration. So right now Wi-Fi integration is working much better. Alright, so 70 million, right? Non-physically accessible to the carrier. Operators provides the Femtocell ID and the customer registers the location and it self-configures. It figures out what frequency to use, what power to use, what preambles to do, what is the ID of the cell, and so on and so forth. And if there are other cells in the neighborhood, everything it figures it out, right? And turned on by consumers. The problem is that even though we can do everything, but the customer can turn off the power. So you thought about there's a neighbor cell yesterday, but there's no neighbor cell today. Right? So topology changes fast, and then it has to optimize all over again. So this is what is called self-organizing. So now you know what is SON mean. SON is self-organizing network. Means that totally hands off. Totally automated. Alright, so management and configuration, self-configuration, remote configuration by service, and that another thing is that the service provider can configure it. They can send some commands from there and say, well, now this guy has not paid the bill, stop the service. You know, the minutes are over, and no more data. Things like that, right? So remote configuration. Femtocell senses the channel to detect neighboring cells and may broadcast messages for the neighbors. So everything is basically remotely programmable or self-programmable. Alright, so much about Femtocell. Now, I think we are going to talk about the same inter-cell interference. But now it's not just inter-cell interference coordination, it is enhanced. So now I noticed another change. They already evolved in the LTE, long-term evolution. So you cannot say LTE evolved because that would be long-term evolution, right? So, so they are using the word enhanced now, everywhere from now on. So everything is enhanced. Enhanced inter-cell interference coordination. It would have been called before evolved inter-cell interference coordination. EICIC is enhanced. ICIC is that inter-cell coordination, but now we have a better one. So it sends a load information message to the neighboring ENB and per physical resource block, and the neighbor adjusts the DL power level at those blocks. So now we are going to do even better than before. Before the UE figured it out that I am getting so much power from here, so much power from here, and that is very long time average. Alright, now we are not going to do long time average. We are going to do frame by frame. In the first frame I got this much, in the second frame I got this much, and third frame this much, fourth frame this much. So every millisecond we have the number of interference. And then we could coordinate by the millisecond, by the frame, by the subframe. So, for example, we could say that I really need to talk to this UE on these two subframes. Okay? And so this guy will not transmit anything in these two subframes. It will transmit what they call almost blank subframe, ABS. And the ABS will simply have a coordination information. So we know that it is not down or it is not failed or anything. It just says, okay, I am there, but I am not talking right now. Okay, ABS, almost blank subframe. And they are there so that the other station can talk to the mobile on those subframes. And so this is called enhanced inter-cell interference coordination. So you can see, and this is continuing for the next 2-3 lectures, that the things are becoming really, really complicated. Now you would think that a little phone that you do has all this logic. Yes, a lot of things are being done in the microsecond, millisecond level to figure out every second what will happen in the next millisecond. So this is EIC-IC. All right, IC-IC was when we coordinated, we did multi-point coordination, this and that. Now EIC-IC is when we coordinate subframe by subframe. Right? It is based upon when we need to transmit and how much we need to transmit. If suppose this guy needs to transmit a lot of information, they will say, okay, please blank out maybe 5,000 subframes. And it will not do 5,000 in a row, it will do every fifth frame or something, so that it can serve its own customer as well. Right? So there is a coordination. So anyway, EIC-IC. Is it clear? Yeah. ABS. ABS is almost blank subframe. So there is data here, there is data here, there is data here. Here there is no data. There is little bit of control. That's why it is not fully blank. But there is little bit of control. This says there is no data. Okay, every frame contains the control and data. Control and data. Control is a map. Control basically says that, okay, in this subframe, the first block is for you, second block is for you, third block is for you. So there is a whole map of what is where the data is for whom, right? So that map will be there, but the map will be blank. It will say there is nothing for anybody here.
What are those pictures of the frames, the blue and the red one?
Okay, so the red one is coming from this tower, blue one is coming from this tower. Red one is coming from the left tower, blue one is coming from the right tower, right? So these are the frames which are coming from the right tower. These are coming from the left tower. But since the left tower wants to talk to this UE, it will use these two subframes to talk to that. And exactly at those two locations, this will not do anything. It will send a blank subframe. Okay? All right. Carrier aggregation with cross carrier scheduling. Now we already saw carrier aggregation, but now there is basically a little bit more complicated one with cross carrier scheduling. So what we are going to do is that there is a control channel. As I said, control channel basically is nothing but the map of whose data is where in this cell. On the other side, basically, there is also a map for the uplink, where in the downlink it will say, okay, in the next uplink frame, you transmit in this carrier frequency, you transmit these carriers, you transmit these carriers at this time. So there is a map for uplink and there is a map for downlink. Right? Those rectangles you saw. So those rectangles are in the map. Map has the information as to what is the username, where the rectangles are, that means what frequency they start, what frequency they end, what time they start, what time they end. That rectangle is specified in the map. Okay? So that is called control. And that whole thing is called control channel. Okay? So here, if you see this, this transmission has two frequencies, blue and green. And the green is the main carrier, primary carrier, and therefore the control is in the primary carrier. Here is the map. This map will indicate to all the users who are in the blue, who are in the green, and where they are. Right? The map covers both the carriers. So everybody, the advantage of this is that everybody listens to only the primary carrier first. If they have something that they have to get, then they will go to the secondary carriers. So basically, physical downlink control channel PDCCH is in the macro cell, and a small cell is sent on different carriers and maybe at a higher power than the traffic channel. So okay, so that's another point, is that there are two carriers, both of them are using both carriers. So this one will use this as the primary, and this can use this as the primary. So when this sends out its signals, it uses this as the primary, the blue one, and the map is here for the blue, for the things coming, for both blue and green coming from here. So whoever the UE is listening to, they will follow that map. But the advantage of using different maps is that now everybody gets the correct map. Because if you got the wrong map, you are in trouble. Right? The data will not be delivered. So the maps, are maybe sent at a higher power and now on different frequencies as well. A UE can talk to both BS using control channels on different carriers. And also the UE can talk to this side using the primary carrier here and talk to this one using the primary carrier there. Yeah.
So the land is like the beacon and the pointer and N and AC. The map. Is it the same as beacon and
beacon? Okay, so we use the word beacon in the wide area network, in the net world. Okay, right? This is telecom world, and so this is not the same as beacon in some senses because I am transmitting the whole thing. Yeah, so the some part of the thing is this using for control. Some of the symbols are being used for control. And so it has the same function actually. I mean, I can see that it is almost the same function because in that control I will say, okay, who is sleeping, who is not sleeping, who should go to sleep, whose packets I have. All of that is here. Okay, but yeah, so they don't call it beacon.